Hello, welcome today to a video explanation of, no, video explanation, 3, 2. Hello, welcome to a video explanation of how we get the wave equation for transverse vibration. This is relevant generally to second year engineering courses where you start to look at vibrations and perform some vibrational analysis. However, you're often given equations, but there isn't a lot of time devoted to getting a good understanding for where they come from. So today I'm going to run you through how we get the wave equation for the case of transverse vibration. First, we should get an idea as to what transverse vibration actually is. So I'm going to draw up a set of coordinate axes just here. And on these axes, we will put a vibrating string. So this is going to be a taut string undergoing oscillations with relatively small amplitudes, and you'll see why later it's important that these oscillations not be too large. So transverse vibration means it's moving kind of like this, and the vibration or the wave direction, if you will, which we call U, is in the vertical direction in this case. So when you look at different types of wave vibration, the wave might not always be moving in the vertical direction. It can be moving in a compressive style in many different ways. So U will be a different direction depending on the type of vibrational problem you're analyzing. But in the case of transverse wave vibration, U is just in the vertical direction that this wave is vibrating. We can also see that there is a horizontal axis going in this way, and we'll label that as X. And we need to define U as a function of other variables before we can actually do any analysis, because what we're interested in is analyzing the height of this wave. And so we'll write U as a function, obviously of X, because you can see that the value for U is going to change along different X positions. It's not constant. And it's also dependent on time, because this wave is going to vibrate and the whole shape is going to change over time. So U is a function of, bit of lag. U, being the height of this wave, is a function of X and of T. Before we can go on and do any more analysis, we need to do what's called, you take a differential element. So a differential element would be that you take a piece of this vibrating string, let's say from just here, and you take a piece that is of infinitesimally small length. What that looks like is you get a string that will be about this shape based on where we've taken it from. And the whole length of this is going to be a length dx because it's an infinitely small piece of string. There are some forces here. Well, there's really just one force, and that is the tension in the string. And the tension is going to come out in the same direction as the string. So on the right hand side, the string started to curve up, and the tension's just going to follow that path. And on the left side, it's also going to follow the path of the string, but we can see that the string started to curve a bit. So they're not going to be at quite the same angles, because that's what allows our string to move. If they were at the same angle, it would just be a straight line. And what we'll do is we'll just say that on the left side, it's at an angle of theta from the x-axis. And we'll say that the tension on the right-hand side is inclined slightly more. I'm not sure if you can see that. That's just theta plus d theta. So it's saying that angle on the left side plus a small increment, which is what our d theta is. And now what we want to do is go ahead and resolve the forces on this infinitesimal piece. So what we'll do is take sum of forces in the vertical direction. And we know that sum of forces is usually equal to mass times acceleration. However, this is a little bit more, it requires a little bit more analysis because we're dealing with an infinitesimal piece. So usually we can say that the mass is the density times the volume of a body. However, the volume of this is not simply base times width times height or anything, because we are taking an infinitesimally small length. Here the mass will be density, but the volume's going to be that cross-sectional area times the length dx. And we can write this because the cross-sectional area is constant throughout the string. It's one of the assumptions we make. And the density is constant throughout the string. So let's go and replace mass here with the density of the metal, cross-sectional area, and that length dx. So A times dx is the volume of this infinitesimal piece. We've also got to write the acceleration in terms of positions that we've defined. And if I scroll up here, you'll see that the vibration in the u direction is what we're concerned with. So we're concerned with acceleration in the u direction. And acceleration is the second derivative of a position with respect to time. So we can write acceleration as del squared u del t squared. And that's just mass times acceleration, but using our coordinate position, our coordinates, I guess you'd call them, and our infinitesimal piece. And sum of forces is equal to mass times acceleration, so now we have to consider the forces on the body. So on the right hand side we've got T, and remember we're taking the vertical components of these forces. So we have to take the sine of the angle. And on the left side of the string we similarly have T, but this time it's acting down. And that's how we get the vertical components. As you may have noticed, the tension is constant throughout the string. So now we need to do a little bit of work and apply one of the best engineering assumptions out there. These are called small angle assumptions. And it goes like this. Sine theta is equal to theta. Now this will make most mathematicians vomit and physicists will run for the hills, but us engineers like to make life simple. And so one of the approximations that we can usually make, if you've never seen this before, is that for very, very small angles, sine theta is approximately equal to theta. It then follows that for small angles, cos theta is equal to 1, and tan theta is equal to theta. If you're not familiar with this, I'd search up another video explaining the logic behind the small angle assumptions, but this is what we can use as a little trick in engineering. And so let's go and clean up our sum of forces now that we've got these assumptions down. Whoop. Good stuff. How much easier is that? What you might notice as well is if you expand out these brackets, those t times thetas are going to cancel out. And so what we're left with is rho a dx times acceleration is equal to t d theta. For the next part, to make a little bit more sense, I'm going to divide both sides by dx. So we will end up with d theta dx. The next thing we're going to try and do is get rid of theta and have the right hand side in terms of u and derivatives of u with respect to x. And the way we do that is we recall how we have defined theta. If we go back to the free body diagram, I'll write this in blue. Theta is an angle between dx and a height du. Well, rather, sine theta is equal to du over dx. And I'll draw another little diagram in case that wasn't clear enough. Theta is defined as this angle here between dx and du, remembering that y is u in this case. And our small angle assumption lets us just turn sine theta into theta itself. But in this equation, we have got d theta dx. So the way that we can turn theta into d theta dx is we can derive both sides with respect to x. So deriving theta with respect to x will give d theta dx. And if we perform this operation, we'll end up with del squared u del x squared. And I've just changed it to the del notation because that's what we use for multi-variable functions, or derivatives of multivariable functions. Partial derivatives, I guess. Yeah, that's what they're called. Okay, let's go substitute this back into our force formula. Now we have it. Often we will clean up this row A and just write it as the mass per unit length. Literally just this. You'll see it written on formula sheets and maybe in some texts. And not only that, but we try to get d squared, the del u del x, on its own and a constant in front of del u del t. What I mean by that is we want to just have on the left side del squared u del x squared is equal to ml on t del squared u del t squared. Formula sheets will not usually have it in this form though. Usually the right side will look like this. And so now we know that when we see something on the formula sheet that says 1 on cs squared, that cs is actually just square root of the tension divided by the mass per unit length. That's all it is. But they don't like to write all of the variables out on the formula sheet because then you wouldn't have to learn the course. You'd just read off the values and substitute them in as is. Okay, and so we have the wave equation. We'll write it a little bit more cleanly. And there we have it. Now though, this isn't particularly useful for, well, it is useful for problems, but we need to do a little bit more work to be able to properly apply it to solve a transverse vibration problem. Namely, we need u as a function of x and t that we know, not a partial derivative relationship. And the way we go about this is we go back to our original definition of u as a function of x of t, and we apply what's called the separation of variables. So we say that we've got this function, which depends on x and t, and we can actually write it as a function of x and a function of t multiplied by one another. And what we're going to try and do now is apply this definition of u being the product of two single variable functions. We're going to try and pop that back into the wave equation. So to do that, we're going to need to derive u twice with respect to x and twice with respect to t. And to keep things clean, I'm just going to use the apostrophe notation. Remember that the q of t and p of x stay there because they are constants when we are performing partial derivatives. Okay, and now we're going to go back and substitute. Now we're going to want to get these functions that are of x and the functions that are of t to be all by themselves on one side of the equation. So on the left side, we want all of the x's, and on the right side, we're going to want all of the t variables, the t functions. And so if we divide both sides by q of t and p of x, we will end up with p double prime of x divided by p of x is equal to q double prime of t on q of t. It's standard. The way that these problems are solved usually, you move the cs squared to be with the x variables. So we'll also multiply both sides by cs squared and end up with this. Cs refers to the wave speed, I believe. Now, a little bit of your thinking cap is needed right now to understand the next step. On the left side, we've got a number times by function of x derived twice divided by that function of x. And on the right side, a function of t derived twice divided by a function of t. Basically, a function of x is equal to a function of t. The only way this can be possible is if both sides are equal to a number, a constant number. Because if either of the sides was equal to a variable x, so if, say, the left side was equal to x and the right side was equal to t, there's no configuration we can come up with that will make them equivalent because x is not t, they're separate variables. So we know that it's got to equal a number, and I believe it was Leonhard Euler figured out actually what this number is, and it takes someone a lot smarter than myself to do this. So take it as gospel. It's equal to the negative square of the natural frequency. And now what we're going to want to do is attack that left and middle equation separately. So we're going to want to have a look at p of x is equal to negative omega n squared first, and then q of t is equal to negative omega n squared. Look at them separately. And because q of t just has functions, not this other variable cs squared, let's look at that first. Next, we're going to multiply both sides by q of t. And we're going to collect terms so that all of them are on the left side. And this may be familiar to some of you. This is an ordinary differential equation. Actually, it really should be familiar to you. And the way we solve this is by taking the characteristic equation, I believe it's called. I've never been too crash hot on getting the terminology right because it's just words at the end of the day and we're dealing with numbers, right? So the way we'll solve this is by a method you should have learned in a maths class. I'm not going to explain it, but look up ODE solutions if you don't get what I'm doing. And then we're going to want to solve for the lambdas. And we're taking the square root of a negative number, so we will end up with plus or minus omega n I. When the solution to your characteristic equation is complex, when it takes this form, the solution to your original, function, f of x, is always going to be e to the ai a sine x plus b cosine b of x. But we're quite lucky because we don't have an a. A is equal to 0. So in our case, for q of t, we get e to the 0 I, a sine, and b here is omega n for us. And e to the 0 times I, well firstly 0 times I, 0 times the square root of negative 1 is 0, and e to the power of 0 is 1. So we're left with a sine omega nt plus b cosine omega nt. Now we need to go back to the top and we're going to analyze the function of x. Okay, and like before, we want p double prime of x by itself on the left. Well, before it was with t, but now it's with x. But I think you get what I'm saying. And to clean things up a bit, we're going to replace omega n on cs with another variable. We'll just call it k. And this will just make it look a little bit cleaner. So if we move the right-hand side of the equation over to the left, we end up with and much like before, we solve the characteristic equation and end up with this as follows. The only difference now is instead of above where we had plus or minus omega n I, instead of an omega n we have k. And so our solution will be the same as q of t, except instead of having a sine omega n t, we'll have a sine kx, remembering that it's literally the same solution except k takes the place of omega n, and we're working with p of x, not q of t. And I'll write it as C and D as the constants because we've already used up A and B for Q of T. Oh, not B. All right. And what we were aiming to do all along is express U as a function of X and T in a way that we can really use it. And we wrote that as P of X times Q of T. And so now if we just substitute in the solutions for P of X and Q of T, we'll have our answer. So we'll end up with A sine omega nt plus B cosine omega nt. Zoom out a little bit. Multiplied by C sine kx plus D cos kx. And there you have it. That is the general solution to the wave equation. And here it's for transverse wave vibration, but you'll end up with something pretty much similar for the longitudinal vibration case. And the way you'll usually see it written on a formula sheet is you'll be given this, you'll be given the wave equation as well. But if you don't do your homework, these will be totally useless to you because you have to recall that K is equal to omega n on CS, and that CS itself is not just a property, if you will. It's related to the tension and the mass per unit length. And generally what you'll do is you'll solve these problems for the natural frequencies, but as long as you understand how we got that equation that's at the top of your screen now and what K and CS actually are, you should be okay. Good luck.